Alright, so this last type of solution is going to kind of piggyback on what we already talked about with acid-base properties of salts, but we're going to now know how we can quantitatively determine that they are acidic or basic using the same things that we've kind of done with acids and bases so far and pH. You're still going to have to figure out which ions have the best effect on the pH, and since those are mostly going to be weak ions, you're going to have to use your Ka and Kb values to determine the pH. So here we have NH4ClO4 and NaOCl. So if I start with NH4ClO4, I know that NH4 plus is coming from something weak, while ClO4 minus is coming from something strong. So therefore, this particular salt is going to be acidic, while NaOCl is coming from a metal ion, which is strong, and OCl minus, which is a weak ion, so therefore it would be basic. So the part that's going to play a role with NH4ClO4 is the NH4 plus. When I add that to water, it can only donate a proton, which is where we see the hydrogen ions being generated. So your K expression would be the NH3 and the H3O plus over the NH4 plus, and you should be able to get the Ka value from your chart. Now I kind of took a shortcut with this one because if you've done a few of these now, I'm hoping you're starting to see that the K value is always going to be equal to x squared in these particular scenarios. You don't have any products over the original concentration of your weak acid or base. In this case, it's 0.4. So if I solve for x and I get that concentration of 1.5 times 10 to the negative fifth, I'm getting my hydrogen concentration, and therefore I can use that to find the pH of my solution, 4.82. If you don't quite get how I went from the equation to my K expression, you can set up an ice chart, but it's going to be the same as you've seen before. 0.40 because there's one ammonium and NH4ClO4. 0 is for the ammonia and hydrogen ions. NH4 is going to go down by x. Ammonia and hydrogen ions are going to go up by x. So you're going to be left with x's on the product side as x squared. And 0.4, since we get to ignore the x that is subtracted away from the ammonium concentration, we are allowed to assume that that x is negligible. We're going to follow the same idea with NaOCl. Since sodium doesn't have an effect on the pH, we're going to only use OCl minus. OCl minus has no protons to donate, so it has to be acting as a base. So it accepts the proton from H2O, making HOCl and OH minus. So I went and found the Kb for OCl minus on my Ka-Kb chart. Again, I only had OCl minus to begin with. HOCl and OH minus started at 0. So I can use my Kb value to equal the x squared over 0.45. And when I do the math through, I can see that x, the hydroxide concentration, is 3.6 times 10 to the negative fourth. Because that's hydroxide, I need to use that to find pOH, 3.44. And then I have to take 14 minus that value to get the pH, 10.56. At the beginning of this slide, I said that NH4ClO4 would be acidic because of the weak ammonium ion, and it was indeed when you calculated its pH. And that OCl minus would be basic because of the weak anion, and the pH indicated that as well. Alright, so this is just using what you've done so far with weak acids and weak bases. And with what we just talked about, you now should be able to do the pH calculations of your salts.